never has to get open. Now the reality is you won't be able to do it the first couple times that way. Right? So keep practicing until you can do this problem again. Now, let's back up all the way to the beginning. Bradley, what wave function, what stationary state did you say should be the biggest?
Second from the angle 2.
And is that true? And so look, what's the biggest one? The second one. The projection is the biggest, right? Because this next projection is a half of this projection.
And what was that? 2 pi x over what? Sine of 2 pi x
over A. Yeah.
So like the Fourier analysis of the step function, visual.
Okay, so Bradley, you're seeing it as a Fourier analysis, and that is the correct way to see this. This is literally an expansion onto a complete basis set. Where did we get the complete basis set from?
Solving the infinite well.
Yeah, we got it from the infinite well using separation of variables. That's it. You nailed it. That's the whole story in a nutshell here, guys.
So, if we wanted to figure out this problem, starting from nothing, we would have to do separation of variables to prove everything. But do separation of variables, find the time independent piece.
Yep.
Then we'd have to
solve the time independent Schrodinger.
Yep, solve that.
And then you would have to use these ideas
in order to, with the parameters,
Yep.
do all that work
Yep.
in order to find Cn, and then go back and plug everything in.
Right. And every single aspect that Mike just mentioned, I expect every one of you guys to be able to do with the book closed. Period.
It's a lot to do one problem.
Yeah. Keeps you busy. It's taken us a couple days, but this is it. If you can do this, the rest of the problems just... So now we'll go, okay, we're going to do a harmonic oscillator. Find that potential. Then we'll find the basis set for the harmonic oscillator. And then once we have the basis set for the harmonic oscillator, what will we do? Instead of using this for the 1D well, we'll use this for the harmonic oscillator. Then we're going to do the hydrogen atom. Instead of using this for the 1D well, guess what this is going to come from? Hydrogen atom. Turn the crank. You guys got it. Go ahead.
So we went back into psi then, or psi of x equals the summation of c spin psi spins, right?
Okay, so where are we?
Yeah, right there. And then we're saying that all of that stuff you have circled below is the c sub n.
No, this stuff is c sub n. So c sub n is just this stuff. This is c sub n. This is c2.
Okay.
This stuff is psi.
Okay, so the psi has the time-dependent piece with the sine
right here.
pi psi. Okay.
Psi2.
When you circle that, I thought you had it all pointed to C2.
No, sorry about that.
All right, no worries.
Yeah.
Thank you.
Yeah.
Okay.
And then,
Look, this is messy. So your job now is to go home and nail this in your notes. You've done every single step. You're confident that you can do this simple integral that you had to do years ago. But if you get it wrong, everything's wrong. So don't get it wrong. Yeah.
Are there any more examples in the book that you recommend, like, you get more examples?
I just gave 3.
I know, but
They're exactly, there's 2.2, 2.7, and this one. And what's the only difference between all 3? What is it?
Psi of n.
Psi of n is the same. It's an infinite. They're all infinite wells. So they all have the same basis.
Only C of Cn is different.
The only thing that comes out different are the CNs. And the only reason the CNs come out differently is because the initial condition looks different. That's it. It's 3 problems where this is the only thing that's different.
and the infinite square well is 0.
What's that?
Infinite is 0 in the infinite square well.
I don't understand what you're saying here, brother. First.
I'm sorry, forget.
Okay. Everybody got it? But as physics majors, I expect you to be able to do everything that Mike said, which is this whole story. Okay, we're done. I can't say it anymore. I can't say it any better. All right. I'm looking a little bit better for YouTube today, so I'm a little bit excited for that. I looked at the YouTubes, like I said, that Jeremy had when I was sick, and I was sick for like 3 weeks, it turned out. I looked like dead. I mean, it was
bad.
I terrible. I sounded bad, I looked bad, I mean,
I should have done like an After Effect to make it like look all grainy and make you look pale.
yeah, I needed your movie production there, Jeremy, for a little makeup and everything like
Who does
that.
makeup? You have some contractor for that? Or?
He casually thrown in the 1930s Nosferatu filter.
All right,
And
guys,
actually
everybody
play the
get it?
engines with his
This is what this
counter
course
alarm.
is about. Now we're going to do some details. We'll do a little bit of formalism.
We're not doing that, are we doing that now?
Yeah, well, no, we're going to do a couple other potentials. Okay, so check it out. So now we're going to do the harmonic oscillator. And this is probably the most important.
Why is that? It comes up with so many things.
Yeah, and I will try to explain that. Okay,
You
so
say it like you say.
this is in joules. V for the Schrodinger's equation is the potential energy, right? Everybody remember? Okay, so the potential energy looks something like this. All right? Now this is going to be a harmonic oscillator potential, but here's what I'd like to do. Let's take a look at this. This is at some x equals 0, where it's a minimum. All right? And this is the potential at this x equals 0.
Now, what would that be? The potential difference. What would that be due to, like, based upon its position?
It's a position, so that's what I hope to explain, okay?
Is it an electric field or something?
It could be an electric field, sure.
All right.
Okay,
Could be.
so let's look at this. Let's take a Taylor series expansion of v of x about x0. So look at the Taylor series expansion. About x0. And again, if you can't do the Taylor series, then we have a problem. All right? So let's take the Taylor series about x0. So what do? The Taylor series means that v of x about x0 is equal to what?
Infinite string of
It's going to be equal
functions.
to?
1 plus.
No. It's going to be equal to v of x0 plus the derivative of v of x with respect to x evaluated at x0 times delta x. I mean, I could write it like this. How about if I write v of x plus delta, v of x plus x0? So remember, what a Taylor series expansion means, guys, if you don't know it, what a Taylor series expansion means is it says, what if I know everything about a function at one point? So if I know everything about this function at x0, I know v of x0, I know the first derivative at x0, I know the second derivative at x equals 0, and so on. Can I build up that function away from x0? All right, a Taylor series expansion. So a Taylor series expansion is derivative of, it's like f of x plus delta x equals f of x naught plus derivative of f with respect to x at x0 times delta x plus 1/2 the second derivative of f with respect to x squared evaluated at x naught times delta x plus so on and so forth, right? That's more familiar, that form? Look what it's saying. It's saying if I know what the function is at x0, I know what the first derivative at x is at x0, I know what the second derivative at x0 is, then what I can do is I can build up this function from what I know at x0. Okay, I'll give you a more pictorial explanation of this. All right? What this says, say I have a function like this. Here's f. Right? and here's x0, and here's f of x0. What I want to do is I want to build up f of x plus, well, x0 plus delta x. So this would be delta x. Right, that's the difference right there, delta x. I want to know what the value of this function is at delta x